There you go. That should work.
Yeah.
Okay, yeah, now it says the live stream is upcoming. So
Okay, perfect.
that's okay.
Okay, this is the one I need to mute.
That should work. Yes. Mute
Okay.
the YouTube.
Yeah.
Okay. And then
All right, go back to Zoom.
You're live.
Okay. All right, welcome everyone, and apologies for the little delay getting started here. A couple of technical difficulties. Hopefully everyone is able to join us here. We'll get started with our virtual speaker series for February 2023. Today we are delighted to have Eileen Straube joining us from Germany. So just a couple of kind of technical things before we get started here. If you have questions for Eileen after you have watched the presentation, feel free to pop them into the chat there, and we'll get to them after the presentation. So just to introduce a little bit more of about Eileen, she's a PhD student at the University of Bayreuth in Germany. Her professor is Dr. Manuel Steinbauer. And her basic PhD topic is understanding the interaction and extinction of organisms in dynamic environments by analyzing the paleontological record. So Eileen also has a master's degree from the University of Friedrich Alexander University in Erlangen-Nuremberg, as well as a bachelor's degree from the same university. Her current research focuses include reconstruction of the paleo environment using geological proxies, understanding extinctions and what controlled them, organisms' response to environmental and climatic disturbances, and using information from the past to predict the future. So she's done a variety of fieldwork, including fieldwork in Switzerland, Sweden, and Germany. And we were delighted to have Eileen here as one of our summer staff at the Philip J. Currie Dinosaur Museum in Northern Alberta in Canada. And so with that, I'll turn it over to Eileen, who is going to tell us about reefs through time.
Thank you. I will share my screen. You should probably be able to see it now. All right. Yeah, so thank you for the introduction. And yeah, I will talk about reefs through time today. And therefore, I would like to take you on a little time travel more than 500 million years back in time to see how reefs looked like back then and how they developed from there to the reefs that we know today. But before we start, let's talk about what actually is a reef first, because this might not be as trivial as you think. If you ask different people, they probably give you a different answer of what they think a reef is. For example, a mariner would say a reef is a rock in shallow water that might damage the ship, whereas a diver or a fisher who are interested in catching or observing a lot of fish, they would say it's a three-dimensional shallow water structure with plenty of fish. An ecologist on the other side who studies ecosystems, they would say it's an extremely diverse marine ecosystem built by stony corals in warm, low-nutrient waters. And me, as a partly geologist, I would say it's a laterally constrained limestone structure created by the growth or metabolic activity of sessile benthic organisms. So organisms that cannot move and that live on the seafloor. So as you see, there's quite a wide variability in terms of definition here. But common attributes of a reef are that a reef is a structure which is built by in situ, so non-moving organisms. It's a rigid structure built by those skeletons of those organisms and or early cementation. And it shows a high density of organisms. So we have the organisms from all domains of life, which are having complex biological interactions. So now when we think about reefs, we often think about those tropical warm water reefs, like the one we can see here in the picture. But do reefs really occur only in the tropics? Definitely not. So on the left here, we have a map which shows the tropical warm water reefs. So reefs that occur in the tropics and subtropical regions, like the Great Barrier Reef, for example, or the reefs in the Gulf of Mexico. And on the right, we can see a map which shows the cold water reefs. So reefs that occur in colder waters or also deeper waters, like we can see here in the north of the Atlantic or south of Australia. So those cold water reefs are also built by stony corals. And like tropical corals, they also provide a habitat for other species. But those cold water corals, they do not require zooxanthellae to survive, which means they do not need light to produce their energy to live. And this is very important because when you live close to the poles, you will probably not get a lot of light. And if you're then living even in deeper waters, for example, you might not get any light at all. Another difference between warm and cold water reefs is also the structure. So for warm water reefs, we know these kind of traditional complexes, but cold water reefs, they form more like accretions, which are called patches or banks. The distribution of reefs in general is mainly due to the temperature of the water, which is especially important for the warm water reefs. But it is also controlled by the nutrient content of the water or the aragonite supersaturation, which basically means how much calcium carbonate we have in the water. This is important because most corals form calcareous skeletons, and so they need this calcium carbonate from the water column to build these skeletons. Another important aspect for the distribution is also the shelf area, especially again for the warm water reefs, because warm water reefs need shallow waters, and those are especially in shelf areas. Another important aspect is also the currents. So water currents also influence the distribution of reefs on Earth. So now that we know what a reef defines and where they occur, let's take a look at the organisms that we can find there. So here are a few reef dwellers from today, so from the reefs that we know from today, like bivalves, for example, fishes or crustaceans, but also sponges or gastropods. So those are organisms which actually live in the reef, but they do not build the reef. As we saw before in the definitions, organisms who build the reef, they contribute with their skeleton to the structure of the reef. And like I already mentioned a little bit, those are corals for today. So here we can see, for example, Acropora. So corals are the main reef building organisms for today. But throughout Earth's history, corals haven't always been the main reef builders. So on this slide, you can see all the reef building organisms throughout the last 500 million years, or let's say the most dominant ones. So of course, there were also corals, but we had also times where, for example, sponges were the main reef builders, or bryozoans. For those who don't know what bryozoans are colonial organisms that are formed out of individual zooids. So one zooid is very tiny, so you would probably not be able to see them, but as a colony, they are relatively large, so they get very easy to spot. So one individual zooid consists of a soft body with a protective shell, and surrounding the shell, we have then the extractozooidal skeleton that we can also see here in the picture. So they look a little bit like corals, but they are actually not. But then there were also times where, for example, bivalves were main reef builders, or microbes or calcareous algae. To make this even more clear, we have here this nice graph, which shows us the numbers of reefs per interval over the time. So here's today, and on the left side, we have the Cambrian, so 500 million years back in time. And what we can see in this graph is when we had times during Earth history where we had a lot of reefs or only few reefs, and we can also see during which episodes which organism was the main reef builder. So for example, in the Silurian and Devonian, we had corals and sponges, which were the main reef builders. And then in the Cretaceous, for example, we can see bivalves were the main reef builders. So now that we already have a little bit of an overview, let's start our time travel, and we go back into the Precambrian. So the Precambrian world probably looked a little bit like this. So the Precambrian seas, they had biological reefs, which were produced by photosynthetic cyanobacteria. And those cyanobacteria, they formed structures which are called stromatolites. They are visible here in the picture. And those stromatolites are formed when those cyanobacteria take calcium carbonate out of the water column as well as sediments, and then they bind them together to kind of layers. Those layers get then stacked on top of each other until we have these kind of mound-like structures. They actually do that because, like I said, they are photosynthetic, so they need light to create their energy. And the light levels are higher if you get closer to the sea surface. So they build these mounds to get closer to the sea surface. Those structures, those stromatolites, are actually still present today. We have here a picture from Shark Bay, Australia, which shows those stromatolites that are actually still living today. And here's a comparison picture of a fossil stromatolite, which is more than 2,400 million years old, so really old. And we can see they look still pretty similar, which is very impressive. On the right here, we have also a cross-section through these organisms, and we can see this kind of layered structure that I mentioned before. We have these, those layers are actually a bit wrinkled, so they are not completely even. This gets important later because there's another organism which has a pretty similar name, but it's actually something totally different. So now we move from the Precambrian into the early Paleozoic. And there we start with the first stage, which is called the Cambrian. During the early Cambrian, most continents were arrayed along the equator, and we had abundant archaeoceatid reefs, which are assumed to be sponges, as well as cyanobacterial reef communities. Those communities especially inhabited the shallow water regions. In this illustration, we can nicely see the transformation from the Ediacaran, so from the Precambrian to the Cambrian, to the Burgess Shale Formation. And what we can see here in the background are those archaeoceatids. So these organisms are actually pretty small. So we can see here in this fossil, this is 1 centimeter and this is one organism. So they were pretty tiny. In this fossil, we're looking from top onto these organisms. If you would look from the side, they actually look like these kind of cup-shaped forms. But they were pretty tiny, but those reefs could reach very huge sizes, up to 300 kilometers in width and 1,500 kilometers in length, which is very impressive. Another interesting thing is that they also had a very variable growth form. So besides this kind of cup-shaped or tube-shaped appearance, they also were, for example, spherical or had this kind of shape. And this is also one hint why researchers think that they were presumably photosynthetic. But also the fact that they were associated with extensive reef structures in tropical environment, as well as their affinity to shallow water habitats, lead to the hint that they were probably photosynthetic organisms, so they needed light to produce their energy. At the end of the Cambrian, an extinction event happened, and those archaeoceatids underwent this extinction, as well as other calcifying metazoans. And following that, there was a global decline in reef building in general, which lasted for 40 million years. You can see that here. So after this peak, we had a huge decline in reefs. And yeah, those periods were also characterized by a warming event and by elevated CO2 levels, which probably contribute to this decline. In the Ordovician then, from the early to middle Ordovician, we had a time where there were still large microbial reef systems dominant. And then in the middle Ordovician, we start with bryozoan reefs that developed. And coinciding with that, there was the Great Ordovician biodiversification event happening, which is also nicely visible here in this plot. So biodiversification means we have a wider variety in species. And this is nicely visible. We can see in the beginning of the Ordovician, we only have these kind of 2 or 3 different reef builders, and then we suddenly have so many different ones. So this biodiversification event is especially characterized by this shift from microbial to metazone reef building, which was facilitated by those skeletal dominated reefs. And yeah, they were then characterized by bryozoans, but also corals and stromatoporoids. Those are stromatoporoids, and they really look very similar to stromatolites, but they're actually something totally different. So a stromatoporoid is an actual body fossil of a once living organism, whereas a stromatolite is a sedimentary structure which is left behind by a microbial mat, so those cyanobacteria. So a stromatoporoid also has a very structured organization. So they build these kind of layers, which have inside these layers, there are vertical lines, which are called pillars. And those organisms in general are assumed to be sponges as well. So when we look now at the distribution of Ordovician reefs here in those maps, we can also nicely see the biodiversification event. So in the early Ordovician, there we can see there was not much going on in terms of reefs. We can see there were mainly those microbial reef communities. And then in the middle Ordovician, we get more reefs, and we can see that there are different reef building organisms like bryozoans, corals, still some microbial reefs, of course, but also sponge reefs. And to give you a little impression of how this actually looked like, here's a nice reconstruction of such an Ordovician reef. We can see here the stromatoporoids and rugose corals, for example. Those are very special because they are actually not here today anymore. So they went extinct at the end of the Permian. And their name comes from their wrinkled appearance, because rugose is Latin and means wrinkled, and their outer shell has some kind of wrinkled structure. In the late Ordovician, we then got the so-called Paleozoic fauna, which had diversified and formed reef complexes, which were dominated by corals, but also stromatoporoids. But we also had a variety of filter-feeding organisms, such as bryozoans or brachiopods. So brachiopods actually look pretty similar to bivalves, and they also feed on microorganisms, but instead of having a left and a right shell like a bivalve, they have an upper and a lower shell. So they are actually not the same as a bivalve. Yeah, here is also an example of how such an Ordovician reef looks today. We have here a nice example from Nevada. And yeah, from far away, it more or less looks like a rock. But if you would go closer, you would probably be able to see some of those reef organisms that I just showed you. At the end of the Ordovician, there was then another extinction happening. And after this extinction, the reefs were then dominated by coral, stromatoporoid, and calcified algae associations. So in the Silurian period, we mainly had those kind of reef structures. Here are, for example, two reefs from Gotland, two Silurian reefs. This is one big reef structure, which is maybe 10 to 50 meters high. So very impressive. And here on the right, we can see one of those stromatoporoid reefs with those stromatoporoids sticking out of the wall. Yeah, and to give you a little impression again of how those might have actually looked like, this is a nice reconstruction of such a Silurian reef. We can see the stromatoporoids in the background and the corals here. But of course, I'm always talking about the reef builders, but there were also many reef dwellers during every episode in time. So for example, like the trilobites. So this constellation of coral, stromatoporoid, and calcified algae dominated reefs continued from the Silurian to the Devonian, so to the next stage. So it lasted for around 80 million years and coincided with a super greenhouse interval, as well as high levels of sea level and elevated atmospheric CO2 levels. So this was a very warm period in time. In the middle Ordovician, we then got the so-called mega reefs, which developed into globally distributed and very large-scale systems. We can also nicely see that again in those maps. So in the early Ordovician, again, there was not so much going on in terms of reefs, and then in the middle or Devonian, there were then suddenly appearing several reefs, and we had especially those stromatoporoid reefs, but also coral reefs that were dominant. And here's again a reconstruction of how they actually look like. Probably many of you know this picture because this is actually from the Curry Museum, which nicely shows how such a Devonian reef looked like. So we have here the coralline algae and stromatoporoids, but also tabulate corals, which were very prominent during this interval. I also have some fossil examples for you. So those are tabulate corals. They have this kind of cell-like structure. Then we have those rugose corals, which have this wrinkled outer appearance. And then a few reef dwellers like the brachiopods and also crinoids. Crinoids are also called sea lilies, which is maybe a more common term. Yeah, so during the late Devonian, there was then another mass extinction happening, which led to the decline of reefs, and then the reefs globally terminated shortly before the end of the Devonian, like you can see here in this plot. So shortly before the boundary to the Carboniferous, we then had only very few reefs. So after this event, the reef builders were mainly limited to scattered sponge and microbial associations, and we also had some rare stromatoporoid patches. But yeah, the Carboniferous then started with a lengthy icehouse interval that was generally characterized by a lack of large-scale and coral-dominated reefs, as well as framework reefs were very rare. So those reefs in the early Carboniferous were dominated by calcified algae, sponges, but of course bryozoans, and non-colonial invertebrates like echinoderms, like sea lilies, for example. So in the late Carboniferous to early Permian, we then had reef-like structures that had some corals, as well as abundant calcified algae and large foraminiferas. You can actually see them here in the picture. They look a little bit like pebbles, but they are actually organisms. They are single-celled organisms, and they commonly produce a calcium carbonate shell. So they can be benthic, like the ones here, so laying on the seafloor, or they can be pelagic, so floating around in the water column. In the latest Permian, we then had reefs that were characterized by a very wide variety of organisms, like calcimicrobes, foraminifera again, sponges, but also bryozoans, algae, and many non-colonial calcifying organisms such as brachiopods and sea lilies again, so crinoids. But we also had some small patches of rugose corals. And like I already mentioned, those rugose corals, they went extinct at the end of the Permian. And this is actually what's coming next, a huge extinction event at the Permian-Triassic boundary. So this extinction event was the largest mass extinction that ever affected the marine ecosystems. It basically eliminated all corals, stromatoporoids, and calcified algae, and of course the reefs that they built. As well as, of course, terrestrial biota were also affected, but since I'm talking about reefs, I will not go into detail there. Yeah, so this mass extinction is associated with enormous volcanism, which contributed CO2 to the atmosphere and to the oceans. And this led then to a dramatic warming as well as ocean acidification. And we also had a marine anoxia, so an event where there was no oxygen in the water, which is very toxic for organisms in general. After this major extinction event, we start into a new era, which is called the Mesozoic. And the Mesozoic in general was a time where we had major fluctuations in CO2 content of the atmosphere. And this also led to the occurrence of several extinction events in the Mesozoic. So the first stage of the Mesozoic is the Triassic. And in the Triassic, the reef ecosystems developed in 3 steps. So in the early Triassic, we had a Metazone reef gap due to the mass extinction, which happened shortly before. And then in the early to middle Triassic, the first reef patches and mounds and shelf edge buildups started to build and were diverse with microbes, encrusting foraminiferas, but also calcareous algae, sponges, corals, bryozoans, but also bivalves. And I have here a nice example. So this is a Placunopsis bivalve reef from Germany. And yeah, we can nicely see this reef structure here. And this is assumed to be one of the first bivalve reefs in the Triassic. So we can see here those bivalves and a close-up very nicely. In the middle Triassic, we then got a biotic turnover among the reef faunas, which was especially characterized by a change in the corals. So in the middle Triassic, scleractinian corals appeared, which are also called stony corals. And those corals are actually the main reef builders today. So those scleractinian corals in the middle Triassic, they were not reef building, but they started to diversify. And in the late Triassic, they then started to form reefs together with sponges and calcareous algae. So we had very extensive ramps and shelf edge reef complexes, especially in the Tethys Seaway. At the end of the Triassic, you can probably guess it, there was another extinction event happening that led to a collapse of the reef systems. We can see that here again, very nice. So at the end of the Triassic, there was a sudden decline in reef building, which was then followed by the early Jurassic, where we also had a time with only very few reefs. So during this early Jurassic, there were 6 swarming events happening, which are also associated with marine anoxia, so this lack of oxygen in the water. And all of this likely inhibited the reef development in the early Jurassic. So it took the reefs until the middle to late Jurassic until they actually diversified again. So in contrast to modern coral-dominated reefs, those in the Jurassic, they were constructed in different water depths and by a variety of different organisms, including sponges and microbes. So the corals inhabited then the shallow water regions, while hexactinolite sponges lived more in the deeper waters, and lithostid demosponges, they built kind of mud mounds and biostromes in both deeper and shallower waters. Here's also a nice reconstruction of how those reefs probably looked like. So this reef development then actually reached its maximum at the late Jurassic, like I already mentioned. We then had a very high diversity in corals. And like modern reefs, those in the late Jurassic, they were strongly controlled by light, water energy, and sediments. During the transition from the Jurassic to the Cretaceous, we then had another reef builder which appeared, and those are the rudistid bivalves. So those bivalves appeared and they became dominant in so-called stromatoporoid coral rudistid buildups. And by the end of the early Cretaceous, those rudistids then gradually replaced both corals and stromatoporoids. This is also nicely visible here. So we can see we start with those rudists here, and corals were still relatively abundant, and then they gradually take over. And the interesting thing is, unlike some changes before in other reef ecosystems over geological time, the transition from corals to rudists is not associated with a mass extinction. But maybe a few more information about those rudists. So rudists, like I said, they are bivalves and they can have a very diverse morphology. Like we can see here, they can have these kind of box and tube shaped appearance, but they could also be, for example, ring shaped. And they could also vary in size a bit. So some of them were only a few centimeters tall, but there were also some that could get up to 1 meter tall. And another very impressive thing is that these rudist reefs, they could get up to several hundred meters tall and could run for hundreds of kilometers along the continental shelves. So, for example, they fringed the entire east coast of North America from the Gulf of Mexico to Nova Scotia, which I think is very impressive. But these reef construction by rutists, they ceased near the end of the Cretaceous. So shortly before the extinction event. You probably all know that the end Cretaceous is the extinction that killed the dinosaurs, but those organisms actually died shortly before this event. So yeah, then at the Cretaceous Paleogene boundary, we then had this big mass extinction that happened. And after that, we start a new era, which is called the Cenozoic. And in the Cenozoic, the first interval is the Paleocene, and there we had a relatively low diversity in reefs. There were potentially some reef-building corals that were present, but they declined during short pulses of warming events that happened there at the beginning, which eventually led to the Paleocene-Eocene thermal maximum. So this was an event which is characterized by a very rapid warming. And this event was also recently proposed to be a kind of analog to the future global warming. So yeah, the Paleocene was a very rough interval to be a reef builder. By the Eocene time, then corals start to diversify, and also possible symbiont-bearing corals began to form reef-like structures. But in general, the Cenozoic, those corals there evolved very fast-growing and porous skeletons that were capable of a rapid linear extensions and a quick recovery. And we also had a rise in coralline algae during this time, which helped very well in binding the reef framework and strengthening the reef structure. So like we can see those here in the foreground. Those attributes are actually very important because the Cenozoic in general was marked by large and sudden climatic changes, which are connected to warming cooling cycles, plate tectonic movements, atmospheric CO2 increases, and changes in ocean circulation. So there was a lot going on there. After the Eocene, in the early to middle Miocene, we had then a major adaptive radiation of photosymbiotic corals. So the photosymbionts apparently became very diverse and more efficient in their association with reef organisms. In the next interval, the Pliocene, we then got another change in reef ecosystems, which was associated with climate shifts, but which is also due to the disappearance of the Mediterranean reef provinces. So this is linked to the so-called Messinian salinity crisis. And yeah, this crisis happened in the Mediterranean Sea here between Europe and Africa. And during this time, the Strait of Gibraltar, so the connection of the Mediterranean Sea with the Atlantic, got closed. And this led to the partially or completely dry up of the Mediterranean Sea. And so we got huge salt deposits during these times and also evaporites, but this also meant that the Mediterranean reef provinces totally disappeared. Another event that affected the reef ecosystems during this interval was the rise of the Isthmus of the Panama, which basically connects North and South America. And the rise of the Panamanian land bridge changed coral and reef ecology because it cut off the larvae supply to the eastern Pacific reefs, which affected those reefs there very hard. In the last interval, before we are back from our time travel, the Pleistocene, reefs appeared to be very resilient, so they were able to endure global changes and they could reestablish themselves quickly, and they could also keep up with sea level changes relatively well. So for example, there were major buildups in Caribbean reefs, which may have been facilitated by fast-growing, high calcification, but also low diversity assemblages, especially dominated by Alcropora palmata, which you can see here in the picture. And those corals were very well in keeping up with sea level changes. And this was especially important here because during the Pleistocene, we had a major deglaciation. which led to sea level rises. And yeah, species that were very slow growing, they could not keep up with this change and then died. But those organisms were very well with keeping up with the sea level, so they were very dominant during this interval. Yeah, and there we are already back from our time travel to the reefs that we know today, with their nice stony corals as our main reef builders and their high diversity in reef dwellers. Unfortunately, those reefs are currently endangered due to climate change, but that's a whole different story. So I hope I was able to give you a little insight into the development of reefs over the last 500 million years. And yeah, with this, I would like to thank you for your attention.
All right, thank you so much for that fascinating presentation. It's great to know the history of such an important ecosystem on the planet, and it has such a long and diverse history. So we do have a couple of questions that have come through in the chat. So Jackson asks, could the lack of algae in pre-Cenozoic reefs be attributed to a bias against things without hard parts fossilizing based on how common algae is today in reefs?
So he's talking about the fleshy algae, I guess, when I understood it correctly. So basically those kind of reef building algae that I was talking about, those are mainly these calcareous algae, like calcareous red algae, for example. So they fossilized pretty well. And yeah, I'm not sure if I got the question 100% right.
Yeah, he says more or less. There is a comment in German that I'm just going to put in the chat for you.
All right.
Because he will be able to understand it.
Let me see if I can see that one. Oh, he or she is just, yeah, very pleased that there are also German researchers here, and he just thanks me for my time, I guess.
Oh,
so
awesome.
Thank you for this comment. Very nice.
So another question from Jack. He says, first off, fantastic talk. Hope you're doing well. My first question is, how do you diagnose catch up and give up reefs in cold versus warm water in the fossil record?
So how you identify which one is a cold and a warm water reef?
He's using the terms catch up versus give up reefs. I'm not sure if that is a...
I'm not sure what he means exactly, but in terms of cold and warm water reefs, you often see, so when you look at cold water reefs, you have more, the sediment surrounding the reef is different from the ones in warm water reefs, because in warm water reefs, you don't get kind of muddy or more fine sediment, because this is more harmful for the organisms there. But in cold water reefs, since they are not photosynthetic, you have a little bit of more finer sediment there, and this differentiates them. But also, of course, the constellation of organisms that you find gives you an information about if this might be a cold or warm water reef.
So another question, thank you for the talk. I hope I did not miss this while listening in, but were bryozoans ever major in marine reef ecosystems? If not, what conditions prohibited them from doing so?
Bryozoans were actually major in reef building. If I just go back to this slide. So we can see here during the Carboniferous, for example, the bryozoans were major in reef building. But also here in the Ordovician, like I mentioned, bryozoans were major in reef building.
So I have a question about symbiosis. So modern scleractinian corals have symbionts. Is there any evidence that other corals are symbiotic, or is there any way to tell?
Usually you can, so there are symbiosis, it's difficult to tell, because often it depends on how well the fossil is preserved. But sometimes you can tell from the structure of the calcareous skeleton if the organism was probably photosymbiotic. And also the references to if you when you know that those organisms only occurred in shallow waters and only in very warm regions, it's very probable that they were probably photosymbiotic.
And I guess just the last question too. So what can the history of reefs tell us about how modern reef systems are going to respond to climate change and potentials for helping them to recover if we can? Is there any insights into kind of the future of reefs?
Yeah, so you can learn from how they reacted to climate changes in history. You can learn about how they might react to the changes that we see in the future, especially in terms of temperature. Like I said, there was the Paleocene-Eocene thermal maximum here happening, which is kind of an analog because it happened very rapidly. So the most difficult thing is that you need to find a climatic event that is very similar to one that we see happening today. And this is not so trivial because most of those events that we can see in the history of the Earth, they happen over very long timescales. And so then they are not very useful because the timescales are just too different. But there are some studies that focus on using those information of how those organisms react after or before such an extinction event to kind of use these trait information to see how those organisms will probably react in the future, like for corals, or this is also possible for foraminiferas, for example. When we know that some of them are more threatened to climate change because foraminiferas have a very thin calcareous skeleton, and when the ocean gets more acidic, they will probably die very fast because they cannot keep up building their skeleton. And so those organisms are more threatened than others, for example.
Okay. Cool. Another comment or question from Nicole says, also, thank you for a great talk. I've heard of corals being produced. And I think what she's asking is corals being produced and then used to repopulate reefs, presumably ones that have kind of been in trouble in the past. Is there evidence of that happening in the geologic record where corals will like return to areas where they've kind of been wiped out before?
Yeah, definitely. So, I mean, it's also a bit more, the whole system is a bit more complex because the continents change and they move over time. So if a coral reef disappears here and then the continent moves, if there is kind of, I mean, would you say that it appears at the same latitude or again at the same, it's kind of difficult to say if they appear at the exact same place again. But of course, they kind of vanish and then appear again. Like we can also see here, there were, like I said, at the end Permian extinction, almost all corals went extinct, and then they came back again.
Yeah, just another question from Jackson. Today we think of reefs as shallow ocean things. Is there any evidence for deep sea reefs today or in prehistory?
Yeah. So like I already, like I mentioned, this map, for example, shows us the cold water reefs. And cold water does not only mean cold water, but also deeper water. So reefs could actually, appear in very deep waters where there's no more light coming down to the ground. And yeah, so they definitely occur also in deeper waters.
Interesting.
Also in Earth's history.
It's just a follow-up question to that. Is it the organisms that live in the deep ocean around the black smokers, like their chemosymbionts? Would those communities be considered reefs?
I don't think so. I think it depends on the structure, but these main reef attributes that are named here, that it's a structure built by an in situ organism, would not really apply for a black smoker because a black smoker is not an organism itself. But I think it depends on, since I also mentioned there are many different definitions what a reef actually is. So if you ask different people, they probably give you a different answer if a black smoker might be considered a reef or not. But I don't think, I wouldn't consider it a reef.
Interesting. So I don't see any more questions. So thank you again for a truly fascinating talk. And for anyone who is listening, this will be posted on our YouTube channel, so you can go back and rewatch it, or if you want to get someone else to watch it, you can do that as well. We will be back in March. March 11th is our next virtual speaker. We're having Thea Weinberg-Hensler, who will be talking to us about bite marks on dinosaur bones. So that again is
baby hadrosaur.
Baby hadrosaurs. So that is on March 11th. So we hope you can join us for that again. And once again, thank you to Eileen for such an amazing presentation.